So I have not explicitly defined the rotational, all right? So when you, when probably the best way to explain it is that I have used two, which is incorrect. So because the book is using two fundamental definitions, the solenoid and the irrotational, which is like not rotational. So the not irrotational, I have to correct it, means rotational. So whenever your curl of a vector is not zero, is rotational. Whenever the curl of a vector is zero, is irrotational. Whenever the divergence of a vector is zero, is solenoid. Whenever the divergence of a vector is not zero, is not a solenoid. So then, because you have these two cases paired, divergence and curl, there are four combinations, all right? So 0, 0 is solenoid and rotation and irrotational, all right? 0 and not, I mean, you know, you will see that on the basis of the definitions. What I will try to do is to explicitly state the four cases. So the only thing is when divergence of A is 0, solenoid. When the curl of A is 0, is not rotational, all right? So I will write them in a matrix and put them there because obviously it is here, but it's not as clear. So I will clarify it. Okay. And I have them like that because the book had it like this and I did not want to go against it, but I will do a table in its place. And if somebody can remind me, that will be great, or maybe I need to make a note here. So I don't forget. 1 second. Any other comments from past week, or any other things that I should clarify? I appreciate all of these comments because obviously make the notes better and easier, rather now than later when we have homework or an exam, all right? Then you tell me that something was either incorrect or unclear. So correct. Rotational, I don't remember that. Okay, thank you. So today we are going to start with the divergence theorem, Gauss's law that we are going to get from the divergence theorem. And then from there, we are going to solve different problems. So just to summarize, and I will just as a review, I will very briefly just remind you that what we have seen so far is Coulomb's law. So as a review, brief review, Coulomb's law, which gives us the force between two charges. All right, where R is the vector that separates the two charges. Then we defined the electric field, electrostatic rather, but electric field that is due to this force. And this electric field was nothing, I mean, the electric field, of course, due to Q1, say, for example, so we remember here, is force sub E, the electric force divided by Q2, which practically gives us Q1 over 4 pi epsilon naught R times the vector R, and this is nothing else but if Q1 is here, and this is distance R, E is the electric field at this point, all right, EQ1, and as a vector, this electric field at that point is going to be this one, okay? So that's what we saw so far. We talked about coordinate systems and so on, as we were talking about. These to be able then to know how to move from one coordinate system to another, as we will have to do later. At this moment, we are gonna start with a different approach to solving this problem, and we will do it by introducing the electric flux density. Okay, so today we are introducing the electric flux density, which is a very important vector, as important as the electric field, and is nothing else if you are in free space, but a scalar, this scalar, multiplied with the electric field. So it's another measure of the electric field, and we call it electric flux density. Why we call it density? Because, erase this. We call it density because, as you see when I will write the expression for it, if I use the previous expression for the electric field that we got from Coulomb's law, then D will be epsilon naught, and instead of V, we'll have Q. Let's say it's not Q1, it's Q now. And then we have 4 pi epsilon naught R times R. And assuming that the Q is this one, all right, instead of Q1, then practically you have that expression for the electric flux density from a charge Q. So it's a measure of the electric field, but it's a density because there is no epsilon naught there. And even if the electric field is measured in volts per meter, all right, the electric flux density, which is Q, which is E, excuse me, epsilon naught E, in terms of units, and in fact, I don't want to make it equal here. I should probably put this one for units. Then D, in terms of units, will be farads per meter, volts per meter, and that's what does it make it? Farads, volts, meter square. How much is farads times volts? Remember, farads is capacitance, volts is for voltage. Do you remember the relationship between capacitance, charge, and voltage? How much is, just as from previous, do you remember that capacitance is the charge divided by voltage? Remember, C is Q over V? We're gonna see it again if you don't remember it. So practically capacitance units times voltage units, which is F over M times voltage makes Q, excuse me, F times V makes coulombs. And therefore, this is in coulombs per meter square. That is what we call it density, all right? It's not like the electric field intensity, which is volts per meter. This is density. Flux density is extremely important. Why is that? Because now we have a different and in fact to Gauss's law. This is, I have to say here. Okay, so now we introduce Gauss's law, and I will also open here another page to write exactly what is before. But what Gauss's law is telling us is the following. It tells us that this now electric flux density that we have already defined is has this property. The divergence of this flux density is whatever Q it applies to. And since we have seen this Q, so if we have a point source Q, a point charge, all right, where Q is point charge. And this is Gauss's law. So that is a very important property. Why is that? Because we are going to use this to find another way of solving problems. Instead of using explicitly Coulomb's law, all right, which gives us E as a function of the distance, all right, or this is the result of Coulomb's law here, all right, you remember that. This is one way of trying to find electric fields, where what you practically do is, you remember we had two different charges and then we use superposition. That's what the formula we use. This is formula 1, expression 1. But after we have Gauss's law, which in fact also tells us that the divergence of V is Q over epsilon naught if we are in free space. So if we use this formula and what we call the divergence theorem, then we can solve problems a lot easier, all right? So this is another way of approaching the same problems. So here, what does the divergence theory say? And for example, let's start with the point charge Q to explain it better. We have a point charge here. A point charge Q. And this point charge creates, we know, an electric field that goes like that. And let's assume it's in free space for now. Okay. Now, if the electric field goes like that, what other vector goes like this? We say that the field is radial. So this is E. So this point charge creates a radial electric field. What is it? Why is it radial? Because it goes out from the charge along the radius if we consider a spherical coordinate system, all right? And then It only changes according to the radius. So if I go here and consider a spherical coordinate system where the center of the spherical coordinate system is here, and then, for example, it's spherical. So it's something like that. Then practically what we have in this particular case is that the field on this surface, the spherical surface, is the same in magnitude because this spherical surface has the same radius. All right, so everywhere here, 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 there, and there, because the radius is the same, the value of the electric field is the same, but the direction is along the direction of the radius. So this is called the radial electric field. Now, if the field goes like that, also the electric flux density will go like this, okay? Obviously. So it's not just E that goes like that, it's D and E that both go like this. Okay, so what we have to think of this as a sphere. Whenever you have a sphere, and I will, this is another sphere, I will do it in a different way so you can see in 3D. Let's assume that you have a sphere. This is the center of the sphere, all right? And this is a surface on this sphere, all right? And let's use this. Oops, that's not true. This one. Let's use this. This is a part of the surface. And then I will call it for now that I will call it D sub S. Let's assume that it's very small. D sub S. When you are on the surface of a sphere, a finitesimal piece of this surface that we call it D sub S is a vector. Why is that? Because every surface is a vector. Every surface, when you try to express it in any coordinate system, you have to express it as a vector because it has direction. The direction of this surface is perpendicular to the surface at that point and going out. And we show it as a n, lowercase, with a hat. And that's the unit vector going out of that point in surface. So any other point in surface has its own direction. This, let me now go, this is a three-dimensional, all right? Let's assume that now I find another part of the surface like here. For this surface, the direction is this one. All right? So every point on the sphere has a small area around it. That infinitesimally small surface is described by a vector. And for example, we call this a vector. And so D sub S is nothing else, so it's a infinitesimal surface, all right? That's why we have a D in front. D sub S has a value and has a direction, okay? So now, because the Q, the charge is at the center of the sphere, we took a sphere of radius R, arbitrary radius, but we took the sphere around it. Then what the divergence theorem says is the following, that if I take a volume integral of the divergence of D in this volume, all right? So the surface has, of course, the sphere has a surface and has a volume. And let me use a different color for the volume. So say this surface also has a volume, okay? So what this one says is that if I take the volume integral, let me just do this so I can then put it on. All right, so this is the volume V, volume V. All right, so if I take this volume integral, and as a matter of fact, let's do this volume on this volume V, the divergence theorem says that this is equivalent to a closed surface integral of this surface S, all right, that I have considered, of d dot ds, where ds is this one. Okay, now why is this important? It's very important for problems that have a volumetric symmetry. For example, spherical symmetry. A point charge Q at the center of a sphere has a spherical symmetry. All right. You will see a smaller sphere. Let's assume, as we will see later, that the charge distributes over a smaller sphere. The smaller sphere has a spherical symmetry. All right. So every time you have a spherical symmetry, then this surface integral simplifies. And as a matter of fact, the way it simplifies is the following. On the surface, let's assume we have the surface S. On the surface of the sphere, all the electric field values, the magnitude is the same, because obviously the surface has the same radius. All right, the sphere has the same radius, and therefore the surface has the same radius from the center. And therefore, on this surface S, D is constant. And therefore we say on S, on surface S, and you see, I saw that with a vector, even if the direction changes everywhere, but the surface is a vector. We said that every surface is a vector. It might change its direction, but it's a vector. Okay, so on this surface S, D, first of all, is along the radial direction. So you remember how we found it, Q over 4 pi R and R here squared, okay? So as a matter of fact, now I'm gonna use a different formula. Remember this formula with R? And we said we are gonna use this formula here whenever you have a coordinate system X, Y, and Z, or wherever you have to explicitly express the radius in that coordinate system. However, also we said that this is equivalent to Q 4 pi AR over R. All right, you remember that also other expression? Where on this particular surface, how does AR compare with N? How do they compare at one point? Let's assume that we are at this point. N is this one here. How much is AR at that point? What is the radial direction if I am at the same point here? I go in the same point and I'm looking at the radial direction. Is it not that N hat is the same with the radial direction at that point? Okay, so these two are equal at point, say, O. It all can be at any place, at any point on the surface. all right, which is on surface S or on surface S. Okay, so you remember that. All right, so now let me take this expression, which is the divergence theorem, and I will take the second part. So therefore, from the above, what do we have? We have that this closed surface integral of d dot ds is equal to, I will do it slowly, is d dot a ds, excuse me, yeah, and is equal to the closed integral of d dot n ds is equal to the closed surface integral of d dot ar at that point, all right, ds. And then from here, we go here, and what do we have? Then we have that this integral is nothing else but q 4 pi 1 over r ds. So now we removed all of the vectors and we have a scalar in the integral. Let's think how we write the surface integral in cylindrical coordinates. So, excuse me, spherical coordinates. In the spherical coordinates, we have what? In spherical coordinates, you remember the 3 directions? What are the spherical coordinates? They have r, theta, and phi. All right, and if this is, say, a sphere centered here, this is the z-axis, this is an x-axis, this is the y-axis, and let's assume that this is point O. So O is here. Let me do this point A. Well, no, let me erase that. Let's keep that point O. So we connect this point. We connect it with the center of the coordinate system. And then that is R, all right, the radius. Then we find the, on the XY axis, this line where this point projects, and this is phi. And this is theta. Theta. So in a spherical coordinate system, the 3 coordinates is r, phi, theta, and phi. Okay. Now we are on the surface, obviously, and now what we have to do here, it is getting very simple though, because we are on the one surface that has one radius. So everywhere on this surface, the radius is constant. So I can go here and I can take the whole Q 4 pi 1 r And then I have this one. So I want to find the surface of the sphere. How much is the surface of the sphere? In fact, I missed here, I forgot the square. How much is the surface of the sphere? You remember? 4 pi? No, that's volume. Surface. Four pi r squared. Okay? Surface of a sphere is surface of sphere equals 4 pi r squared. Okay, just to be r squared, where r is the magnitude. Let me clean it up here. Okay, so if I take 2 and 3, from 2 and 3, what do I get? That finally this one, where I started, is nothing else but Q. All right, if I plug 3 into 2, I find a very important, that the volume integral of the divergence of D on this volume is equal to the charge that is surrounded by this volume. Okay, and this is very important to remember because we are solving problems with that. Now, when does this apply? That applies if there is a spherical symmetry in the problem. All right. Now, if you have a spherical symmetry in the sources, rather, because if your sources cannot be placed into a space that is spherically symmetric, create a spherically symmetric problem, then you're not going to be able to do what we've done here. However, for this particular case, and for a number of cases we'll see from next, this is an extremely important formula. All right, and in fact, so we proved it here. All right, but here I just remind you the divergence theorem. Okay, and it applies not to this original theorem, applies to every volume. It applies to every source. But the final result that we got here, the way we did it, it applied, the approach we took to demonstrate it applied to, because the problem was spherically symmetric. But the general formula applies to any vector, all right? So this is just exactly what I said. You see that, that's for your notes, all right? And then here, this is what we derived, as a matter of fact, today. I will rearrange those notes when we try to, when I put them. This is another also, as you can see here, demo of the same thing. And in fact, you can start with Gauss's law, and from Gauss's law, you can rediscover Coulomb's law. So practically, and of course this is true because all of the formulas we are using are reciprocal. All right, when you go from one formula to another, you can reciprocate. You can derive, say, if from one, which is Coulomb's law, you find Gauss's law, then from Gauss's law, you can find Coulomb's law, all right? That's not, if that could not happen, then there was a mistake somewhere. because everything that we did, all of this, we did not approach what we call functions which explode. We did not, all of these functions are well behaved. All right, so having said that, then these laws apply in a reciprocal way. Now, what I would like to do next is any comments so far. So now what have we learned so far? We remember we started with Coulomb's law. We found forces, we got into fields. Then we stopped there. We solved the problem, all right? Then we solved a problem of one charge and a problem of two charges, if you remember, using the Cartesian coordinate system last time. Now we came back, we said, okay, let's remember again Coulomb's law. Then we introduced the electric flux density. From there, we introduced Gauss's law. And then we showed that from Gauss's law, if I use the divergence theorem, I can find that the divergence of D is equal to Q. And in this particular case, I could find, all right, let me see what I did. We found that, all right, and especially as it shows, so here, another thing. When Q, this is a true that the volume integral of the divergence of D equals Q. But when Q is a point charge, is only at one point, and it concentrates there, it's an ideal charge, all right? Because charges do not, I mean, even microscopically, they distribute. But macroscopically, you can actually make the assumption that the charge, if it's all concentrated in a very close vicinity, then you can say that it's a point charge. In a point charge, so I will take a next step here. Let's see where I was, and I will go down. So, okay, I will do it here. For a point charge, okay, so for a point charge, you can write that this equation above reduces to this. This is true only for point charges, all right, for charges that locate at one point in space. And that is important to remember because it only applies there. And then, of course, this is a total charge and it's a point charge, okay? Now, that is a fundamental property, but here what we want to do is to generalize it because at this point the charge is all at one point. In real life, charges distribute. Even, for example, all of this equipment now, it's all grounded. But if, for example, you did not have grounded equipment, and then you would touch this metal, it would you would feel like a small electric shock because there will be charges here, all right? Positive charges. Now with ground, what happens, we'll see that you neutralize because the ground we said is like a sea of electrons, all right? So if you bring ground here and you ground this, then all of the positive charges that have accumulated here will be neutralized. So I can touch it, or I can touch all of the metal practically. Not before, not the old days. People had to be on a plastic. And a lot of times, even today, you know, for example, have you seen if you use your laptop and somehow it's not connected to any source or anything, and then you put it on something, if you touch it and it has already charged, you're gonna feel it a little bit, all right? Especially if your feet are touching the bare ground, you're going to feel a little bit of something because the charge has accumulated on the surface, and because it's not connected to anything, probably sitting on another dielectric that is an insulator, and then you touch it and then the charge goes directly, or the electrons come up directly and then neutralize it. So these charges distribute everywhere, all right? They're not points. So we have to move away from the point charge. And to be able to move away, we have to introduce what we call the charge density, okay? Charge density. So the point charge here which we have seen so far, is a charge located at one point, and the total, the unit is coulombs. However, in real life, charges do not locate at one point, but they distribute. If a charge distributes along one line, we call it line charge, and is a good approximation for specific applications, but line charge. Then we introduce the line charge density. All right, all of these are densities. The line, now if the whole charge, Q sub L, the whole charge, of course, on this line is going to be still coulombs, but it's called the line charge for now. If it distributes on a surface, the whole charge, even if distributed, is going to be in coulombs, but it's going to be a surface charge, and then a volume charge. Now, when we have charges distributed, we are introducing what we call the charge density. So the point charge, there's no point of introducing a density, is all at one point. But when we go to a line charge, we have to introduce the line charge density. For a uniform line charge density, so for uniform charges, distributed charges, the line charge density is going to be the total charge divided by the length, if it's uniform. And in that case, it's going to be coulombs, with a name here, per meter, the unit. A surface charge density, if the whole charge is uniform on the surface, then the surface charge density is going to be the whole charge divided by the surface area. And that is going to be coulombs per meter squared, the unit. And then you have the volume charge density, which means the charge is distributed in a volume. And if it's uniform charge, then we have the volume charge density, which is in coulombs per meter cubed. All right? So why are those important? These are important because we are going to be able to solve problems, all right? And I will show you a problem that I will be able to solve very quickly. At least a part of it in the next 5 minutes, and then we'll continue with that next time. But here, so consider a volume charge. So problem here, example. Consider that we have, consider a volume charge Q, which distributed, evenly distributed, evenly within a volume V. A sphere, I do like, let me be more specific, within a sphere of radius R equals 3 centimeters rather. And let's assume that Q is 10 nanocoulombs. Okay. We want to find the field, due to this charge at a distance R equals 6 centimeters from center of sphere. So what is the problem here? They say the following. We have a charge here, and the charge distributes now evenly. All right, here. And I have I consider, therefore, since it's a sphere and the charge distributes evenly, the sphere has a radius r, all right, from the center. And this is 3 centimeters. And I want to find the electric field at a distance which is 6 centimeters from the center of the charge. All right. Now, the charge is symmetric in a spherical coordinate system, has a spherical symmetry. All right. That means that I can consider a spherical coordinate system that has the center of the charge. So my whole problem then in that spherical coordinate system remains symmetric. Okay. So according to my previous solutions, what we have is inside the sphere, we have a charge. The total charge is Q. But since it distributes evenly, so my first step is to say that I will have a volume charge density, which is going to be the total charge divided by the volume of the sphere. And how much now is the volume of the sphere? You just told me. Okay. That's the volume of the sphere. So now I can find a volume density, which is going to be 3Q divided by 4 pi r cubed. And because I have Q, I have r cubed, then I can find that QV is going to be, and I'm not going to do here all that, but it's going to be 10 to the minus 9 coulombs. And it's going to be 4 pi r, it's 3 centimeters. So it's going to be times 9. And here we have centimeters cube. All right. And I have also a 3 here. 3. So practically, that gives me 3. And I have 10 to minus 8 divided by 4 pi. Yes. Which one? 6 instead. No, I mean, we're trying to find the Q. What are you saying?
Like 4 pi r cubed.
I put a 9 instead of what?
27.
Why would I put 27? R cube, I'm trying to find the charge density.
That's what 3 cubed is.
Ah, yes, that's what you would. I'm sorry, 3 times 9. Yeah, okay. Forgot my fundamentals. Okay, so thank you. All right, so here, and then 36 here. Pi. All right, so that's C centimeters cube. You can keep it like that until you decide what other dimensions you may have to deal with. All right. So at this moment, what Gauss's law is telling me, all right, I found that you will see, as a matter of fact, what you will see for now is that I don't necessarily need it, but I found that Q sub V because it's important. Gauss's law tells me that the divergence of D is equal to Q, but now because we don't have the point charge, we have a charge density, and it's a spherical charge density, all right? So QV. Now from that, we are going to, I know that you have to go. So at this point, I will stop it. I will continue with this next time, but it's one problem that we are going to solve before we go to the problem next. So we are going to stop here for now. But what we saw today is Divergence Theorem and Gauss's law, and we are going to apply to solve problems, all right? So we'll solve a number of solutions where we'll solve a number of problems where we're going to be looking for the electric field for the solutions for different types of sources. All right, and I will give you an exercise for Wednesday. Today, office hours today, 3:30 to 5:30. You're welcome.
Back to the first page that you were on.
The first page?
Yeah, like when you were reviewing the concepts, I was just confused about something. Should this be R squared or?
Yes.
Oh, okay, cool.
Sorry.
So, and this one should
In fact, it should be R cubed.
it should be R cubed?
Yeah.
Why should it be R cubed?
It should be R cubed because I have an R here. It should be R squared when I have an A sub R.
Oh, okay, that makes sense.
All right, here.
So this should be R. Okay,
Yeah.
perfect. Thank
Yeah.
you so
All
much.
right, thank you. Hi.
Told me to come to class about like my team partner.
Yes, you have not been able to find anybody, isn't it? Is that you? Somebody has, there are a number of people who have not found their team partners. Have you found anybody or not?
I only have one partner on campus, and he isn't like feedback.
And then he is not connected with you. Okay, I will move you to another team because I think what I decided to do, there are a number of people who have been MIAs. I will put them all together in a team. And then they figure it out what they're gonna do. For now, I don't know whether they know what's going on or they care. But can you tell me your name? Yes, I got your email. I know names, but Robert Brown moved to another team. And you know how I'm gonna find why I have not done this yet? Because this is the first time I get team. I receive back the team exams, and then I will see who has not, because I asked students to put the names down on those who participated, and I will see who was not there. And I will put them all in one team. I'll move you around. Do you have any preference? Okay.
Thank you, Professor.
Bye-bye.